Hello, this is the second part of a video summary on curve sketching, just the basics, the fundamentals. We're not going to get heavy into the calculus or even the algebra for that matter. It's just rather interpreting what first and second derivatives say about original function. So here we are moving on then. In an exercise number 5, we're given the graph of a cubic polynomial. They give us the equation, and then they tell us that m is a stationary point and n is a point of inflection. So our tasks: find the derivative, find the x-coordinate of the maximum over there, and find the x-coordinate of the point of inflection, and then finally find the equation of a line tangent to the curve at 312. So this is kind of unrelated, part D, but the first three are talking about inflections and stationaries. So you take the original function and you take its derivative using the power rule. It's really straightforward. And to find the value of m, you need to find when the first derivative equals 0. So you take the first derivative, set it equal to 0, and factor. In solving, I find that x is equal either 1 or -5, and I'm going to assert that m is in x equals negative values. Here's probably where x equals 1, so -5 is going to be the x-coordinate of point m. For part C, I have to take the second derivative, so I take the derivative of my derivative, and I get y equals 2x plus 4. I set that equals 0 to find points of inflection, and I find that it happens when x equals -2. And finally, for the last one, it says the tangent to the curve at the point 312. So I'm going to evaluate f prime of 3 because when x equals 3, I need to know the slope of the tangent line. So the slope of the tangent line is f prime of 3. Turns out to be a big number, 16. Now I know the coordinates of the point on the line, 312, and I know the slope of the line, 16, so I just use point slope, put in 12, 3 for the y and x respectively, 16 for the slope, and a little cosmetics, and we get y equals 16x minus 36. Just to make sure that everything's on the up and up, I went into Desmos, I put in the exact equation that was given to me as shown. I also put in the equation of the line I was supposed to be finding, and here the blue line is in fact tangent to the curve at 312, and the maximum occurs at 5, the minimum occurs at 1, and I didn't show the inflection point, but everything else is right, so I'm sure this inflection point is correct as well. Number 6, here we are asked to find basically when the tangent is horizontal. In other words, we're looking for stationary points, two values of x where the stationary points exist, and for each of the values we have to determine if we have a maximum or minimum. So the first thing is, when does the derivative equal 0? So I find the derivative, set it equal to 0, which requires dividing everything by 3 to make nicer coefficients, and then simple factoring, and we get two values for horizontal tangent lines. For part B, take the second derivative, set it equal to 0, and not set it equal to 0, I'm sorry. What we're going to do is I'm going to take the second derivative and evaluate it at -1 and get -12. So there's a stationary point where the curve is concave down, which means the maximum exists at -1. Then I take g double prime of 3 and I get +12, which means we're concave up, which means we have a minimum at x equals 3. And there's a maximum at -1 and a minimum at 3, and that's confirmed by my graph. So notice I'm using the second derivative instead of the first derivative to determine if we have a maximum or minimum. It's far more efficient if the second derivative is easy to find. Last but not least, we get to the last question on the review packet, and what that does is it gives me a bunch of information about the first, second derivative plus the original function. So what it does tell me is there's a point at 0, -1, and a point at 1, 2, and those points are labeled on the graph for us already. So then what we have to do is determine what's special about those points. So what I see is we actually have a stationary point because we have a 0 first derivative. Positive second derivative means we have a minimum at 0, -1. Above that information, I saw that when x is from -2 to 0, which is, again, where 0 is going to be our local minimum, the function is decreasing, but concave up. So on my graph, I know there's a stationary point here, and then the function decreases, but at a decreasing rate. Or it's going slower, concave up. And then I can see the function is increasing after x equals 0, but still concave up. So I draw a curve that increases but still concave up until I get to the point 1, 2, which is an inflection point. And the last conclusion I make is that we have an increasing function that's concave down. So again, what I did is I took each statement and turned it into language related to descriptors of curves, and I'm looking at concavity and increase or decrease, and that's how I was able to put together all of these pieces. There's a stationary point here, an inflection point here, concave up the whole way until we get to 1, 2, then it's concave down the rest of the way after that. I hope you find this helpful. Thanks for watching, and have a great day.